All right, so this is lecture number 2, part 6. And in this lecture, we'll be talking about limits at infinity, as well as defining properly what horizontal asymptotes are. And this corresponds roughly to section 2.6 of your text. Limits as x approaches infinity and horizontal asymptotes. All right, so we'll start off with an example of what we mean by the limit as x approaches infinity. So let me post a graph. Let me pull one from the textbook. Okay, so let's consider this graph. The rational function typed right here, presented right here, y is equal to x squared minus 1 divided by x squared plus 1. And we are interested in evaluating this limit. The limit as x approaches either plus or minus infinity. Actually, x squared minus 1 divided by x squared plus 1. Now you can tell by the graph that as x approaches infinity, the output approaches 1, but of course it never reaches 1. And as x approaches negative infinity, the output again approaches 1, but never reaches 1. And so we could say that y equals 1 right here is a horizontal asymptote. Okay? And so how do we know that this is true for this particular function? And of course we resort to the old standby, and that is assembling a function table and evaluating the outputs of the function as x grows very, very large and look for a pattern. So for instance, here would be your indicator table function. All right, and so here are values of x. Now, note that this particular function is an even function, okay? And you know that an even function, for even functions, we have f of x is equal to f of minus x, like the cosine function. Well, that holds true for this function as well. So for instance, if I choose, here's my x value, okay? If this is x, and say this is minus x, then notice that the outputs are the same for both x and minus x. And so that's why we can double down on the inputs for this function table, because whether it's plus or minus, we're going to get the same output. And look at the pattern as x grows large. You see the pattern of outputs. Okay, it's getting closer and closer to 1, but it's not quite 1. All right, so this is essentially what the topic, section 2.6, is all about. It's solving these kinds of problems. The limit as x approaches infinity of f of x is equal to a number, say L. Okay, and if this holds, if x approaches infinity of f of x equals to a number, then this is the definition of a horizontal asymptote. Okay, definition of, and I'll abbreviate horizontal asymptote as HA. Okay, and it also holds for negative infinity as well. So we can go to negative infinity. So either way. So a couple of graphical illustrations I can show you. some potential structures that you may encounter in the chapters we'll be dealing with as the semester goes along would be things that may perhaps have these kinds of properties or graphs. And if you've had algebra or trigonometry recently, you can maybe even recognize some of these functions. So here's a function that approaches the horizontal asymptote. As x grows large, y approaches L. So note, look at the horizontal asymptote, which is in this case y equals L. Even though y equals L is a horizontal asymptote for this function, note that the function outlined in blue can still cross the horizontal asymptote. The only requirement for the presence of a horizontal asymptote is that as x approaches, in this case, infinity, y approaches the horizontal asymptote. It has an asymptotic property, that is, the distance between the function f of x grows smaller and smaller, but it never equals 0. In other words, it never touches the horizontal asymptote. So as x grows larger, this blue arrow distance grows smaller and smaller, but it never goes away. Okay? It just keeps getting smaller and smaller as x, numerically smaller and smaller as x grows larger. Now in the next case, say in this middle case, it looks like this may be something of a vertically shifted exponential function. Say like perhaps a possible formula for this blue curve could be, say, y equals e to the x plus L. Okay? And again, or how about say e to the minus x, that is. Okay? So as x grows larger and larger, e to the minus x, of course, diminishes to 0, but it never quite equals 0. And the distance between e to the minus x and L grows smaller and smaller, but it never equals to 0. Okay, and then the third case, you can see this function that has kind of an oscillating property. Although it crosses the the horizontal asymptote an infinite number of times, eventually what happens is the function will cease to cross the horizontal asymptote, and the function's output, the distance between the function's output and the horizontal asymptote becomes smaller and smaller, but they never cross. This would be an example function like this would be, say, something like e to the minus x times a trig function, say cosine x or something like that, or perhaps sine x. These are called damped exponential functions. And I teach these functions in my trig class. So if you have my trig class, you should be familiar with these. And we'll talk about these more later. Okay. Oh, I've got some more. Okay, so some more examples. So let's talk about the converse, say, give you some representative depictions of the limit as x approaches minus infinity. Of a function. So f of x equaling to some output. Okay, so let me pull up some diagrams showing you what those could potentially look like. Let me create some for you. Okay, select the drawings. Okay, so consider these three drawings. So here we have the case where as x grows larger and larger, in the negative infinity direction. That is, x grows very, very small. So basically what I'm saying is, as we move off in this direction, x is becoming smaller and smaller. Okay, like negative 100 is less than negative 90, for instance. So, or I could also say that x grows very, very large in a negative sense, or x grows very, very small. I'll use those concepts interchangeably. But note that the output of the function tracks the line y equals L in an asymptotic sense. And when we mean asymptotic, of course, we mean that the function f of x gets closer and closer to y equals L for each diminished value of x, but it never touches the line y equals L. Look at the second example. In this case, this function exhibits an infinite limit as well as a negative infinity limit. So there are two horizontal asymptotes of this function. And this happens to be, of course, the graph of the arctan function. A very important function that we'll work with quite a bit. So the arctan function is asymptotic with y equals pi halves as well as y equals negative pi halves. Okay. And then again, here's another example of a function that crosses the horizontal asymptote a couple of times at a couple of points, but then it exhibits asymptotic behavior as x shoots off toward negative infinity. All right. So we can do an example. Let's see if I have one. So let me copy the problem. This was a test question in one of my earlier calculus classes. All right, so the question is, well, actually there are two questions. We want to analyze or demonstrate that the limit as x approaches -1 for this particular function equals to infinity. All right, and if that's the case, this would be the indicator of a vertical asymptote. So let's highlight or accentuate x equals -1, which is right here. So if the limit as x approaches a number equals to, say, infinity, as in this case, you can see that it's a vertical asymptote. So here's a VA. However, well, let's see here. The limit as x approaches 2 from the left in this case. So 2 from the left. So that would mean we're approaching from x is approaching 2 from numbers less than 2. And in this case, you can see, well, it appears that the output would shoot up toward infinity, right? Or is that the case? No, I'm sorry. No, that solution is correct. No, we approach 2 from the left. I'm sorry, I got it backwards. We approach 2 from this direction, okay? And as you can see, as we get closer and closer to 2 from numbers less than 2, the output of the function shoots down toward negative infinity. So here again, we have a vertical asymptote. So we're contrasting vertical asymptotes with horizontal asymptotes. Now, how about the limit as x approaches 2 from the right? That is, from x approaches 2 from numbers bigger than 2. Okay, so now in this case it would be, the output would be positive infinity. Okay. All right, and so that's exhibiting a vertical asymptote. X equals 2 is a vertical asymptote. And how about the limit as x approaches infinity? All right, so if this equals a number, then clearly we would have a horizontal asymptote of f of x. Well, in this case, x approaches infinity, right? We can see that we have asymptotic behavior exhibited by this graph right here. So that appears to be this output value, which is 4. Okay, so we'll classify that as 4. And then how about as x approaches minus infinity? Of f of x. right? And that appears to exhibit horizontal asymptotic behavior as well. That appears to be an output of 2 right there. Okay, so that's how all of it works. Okay. Now, this actually brings up a very important theorem that I want to talk about, and it has to do with functions that exhibit hyperbolic type properties. So let me go ahead and post a graph as well as state the theorem. So let me create the one second. I'll have it. I'm almost done writing it up here. Okay, so here it is. Extend the page, paste. All right, so look at the graph y equals 1 over x, which is your classical normalized hyperbola. And notice that as x approaches plus infinity, the output of the hyperbola approaches 0. And also as x approaches negative infinity, the output of the hyperbola approaches 0. And so this kind of property motivates a theorem. And the theorem goes as follows. If some number r, choose a number r, which is greater than 0, and in the case of this graphical example, r is 1, and r is an element of Q. Okay, so what is Q? Q is the set of rational numbers. Q is a rational number. Now, that is, we're restricting r to be a number other than, say, like pi or e or the square root of 2. Those are all irrational numbers. Q is a rational number. Okay. So if r is a rational number and it's greater than 0, then we have this very important structure, the limit as x approaches infinity of 1 over x to the r is equal to 0. Okay. And the assumption is that x to the r is defined for all x. Okay, x to the r exists. For all x. Okay, there's a caveat to that. All right, now what else? Oh, so the theorem has 2 parts. There's this part, the limit as x approaches infinity of 1 over x to the r is 0. And of course, the other part is the limit as x approaches negative infinity of 1 over x to the r is equal to 0. I'm not going to offer a proof, but you can intuitively figure this out by just merely assembling a function table and driving x toward either plus infinity or minus infinity and observing the outputs for any particular r that's restricted to these properties. Okay, so we can do some examples. Couple of limit problems. So next page. Let's calculate a limit. Say the limit as x approaches infinity, and I'll give you a rational function. In this case, I'll have 3x squared minus x minus 2, and we'll divide that by 5x squared, 5x squared plus 4x plus 1. Now, if you recall from your Chapter 1 notes, when we're talking about graphing, we disclosed how to calculate the presence of a horizontal asymptote, and we readily see that 3 is the leading coefficient and 5 is the leading coefficient of the denominator. And then the orders of the numerator and denominator are the same, so all you have to do is just merely take the ratio of the leading coefficients. Another technique that's often useful is we can divide upstairs and downstairs of this function by x squared to validate the claim that 3/5 is the limiting value. So let's do that. Let's divide upstairs and downstairs by x squared. The reason why I want to do that is because I want to demonstrate the validity of the theorem that when the limit as x approaches infinity of 1 over x to the r is equal to 0. And we're going to make use of that theorem right here. So if I do this, now I divide the denominator by x squared. So I can do this. I haven't changed the function. It's still the same function. If I divide upstairs by a quantity and downstairs by the same quantity, I haven't changed the function. Now, is it okay that I do this? Have I run into any trouble by potentially dividing by 0? Well, the answer is no, because the safety part is x is going toward positive infinity. So x in the long run will not be anywhere close to 0. So this division is safe, okay, because of the fact, owing to the fact that we're dividing by a large positive number. Okay, so we'll do the division. So we'll have 3 minus 1 over x minus 2 over x squared in the numerator. And then we'll do the division in the denominator, and we'll have 5 plus 4 over x plus 1 over x squared in the denominator. All right, and then we can, of course, now since the function is defined as x approaches infinity, we're good to go with the limit laws. So we can take the limit operator and essentially distribute it term by term to every term in the rational function. So right now I'm just deploying the limit laws. This is x approaches infinity of 1 over x minus the limit as x approaches infinity of 2 over x squared and then we'll have the limit as x approaches, oops, it got kind of sloppy there, didn't it? The limit as x approaches infinity of 5 plus the limit as x approaches infinity of 4 over x plus the limit as x approaches infinity of 1 over x squared. Okay, now, so now we go ahead and evaluate each of the limits. So we know that the limit of a constant is the constant itself. And we know from the previous theorem, in this case r is 1, so we know that term goes to 0. And in this case, for this limit, r is 2 from the previous theorem. And the limit of a constant is the constant itself. And we know that that goes to 0. And we know that goes to 0. Now I skipped a couple of limit law steps, like for instance I could have taken this 2 and made it a coefficient here, and I could have taken this 4 and made it a coefficient there. So you can do the mop-up work there. But nevertheless, the limit is 3/5. And I can show you the graph. It has a rather interesting graph. See if I have it here. Nope, I don't have it there. So here's what the graph looks like. And as you can see, the function crosses the horizontal asymptote y equals 3/5 once. Right here, you can see it. But in either case, as x approaches minus infinity, the output seeks to 3/5, and as x approaches plus infinity, the output seeks to 3/5, and it happens to cross. So yeah, so here's the asymptotic behavior of this function. All right, so how about we use our understanding of asymptotes to graph a rational function, a kind that you never really saw in your algebra studies. So I'm just checking the notes here, making sure I have everything. Okay, so let me pull up a new page. And so let me type it in. So we'll let f of x equal to the square root of, say, 2x squared plus 1 divided by 3x minus 5. All right, so we want to analyze the asymptotic behavior for this function. So we can start off with an assessment as x approaches infinity for this function. And okay, so why am I analyzing the asymptotic behavior of this function? Well, the utility in doing so is that one of the results is that we can use this asymptotic knowledge to graph the function. And this is a type of function that you probably never could sketch in, say, if you took Math 107 or Math 108. But now, because we have an understanding of definitions of horizontal and vertical asymptotes, we can now do this exercise. So it was a long time in coming. So the limit as x approaches infinity of 2x squared plus 1 divided by 3x minus 5. Okay, so what we can do is, what if I divide it upstairs and downstairs by x? All right, so what I'm going to do is I'm going to do this. Now, again, we don't have to worry about dividing by 0 because x is very far away from 0 because, in fact, x is going toward infinity. All right, so if I did that, now we would have this result. I would like to bring the 1 over x inside the radical. Okay, and since x is positive, I can do that by taking the square root of 1 over x squared. All right, so doing that, I'll have 2 plus, the numerator becomes this after I do the multiplication, divided by, now the denominator becomes 3 minus 5 over x. Okay, so do you see why I multiplied upstairs and downstairs by 1 over x? Because it allowed me to format the function in terms of powers of 1 over x. Because when we format the function in terms of powers of 1 over x, then we can use that theorem. Recall the theorem. This allows us to leverage this theorem right here. It allows us to leverage that theorem, and that's why I did multiplied upstairs and downstairs, so I can get all of the function in terms of 1 over x, powers of 1 over x. Okay, and so now I can use the limit laws. So when I invoke the limit laws, I'll have, well, I can bring the limit inside the radical. Okay, clearly I can bring the limit inside the radical. That was one of the limit laws we discussed. So why don't I go ahead and do that? So we get the square root of the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 1 over x squared get all that's under the radical. And then we divide it by, now based on the limit laws, we can distribute the limit operator term by term. Minus 5 times the limit as x approaches infinity of 1 over x. Okay, so the limit laws allow all of these computations. And then the theorem allows what? Well, the theorem says that that term goes away, that term goes away, and we're left with the square root of 2, because the limit of a constant is the constant itself divided by 3. Okay, so there we have the square root of 2 over 3 is a horizontal asymptote. Okay, so how about we evaluate the limit as x approaches minus infinity? Okay. Yeah, so negative numbers are definitely in the domain of this function. So what do? Well, for x less than 0, all right, we have this. We know that the square root of x squared is equal to the absolute value of x, and which is equal to the minus of x, minus x. Okay, so we have this important result, and we're going to make use of this result. So for x less than 0, okay, 1 over x times the square root of 2x squared plus 1 is equal to the negative of 1 over the square root of x squared times 2x squared plus 1. Okay, and that is simply equal to the negative of 2 plus 1 over x squared. All right, so that's how we transform the numerator of the rational function. And we'll do the same. We'll divide the denominator of that rational function by x as well. So we have this result. The limit as x approaches minus infinity of the square root of 2x squared plus 1 divided by 3x minus 5. Okay, and remember, I want to divide upstairs and downstairs by 1 over x so I can get the function transformed in terms of powers of 1 over x, so I can use the theorem. So that would be the limit as x approaches minus infinity of 2x squared plus 1 divided by x divided by 3x minus 5 over x. Okay. And as we stated above, we had the result for the numerator. So we'll use that result. So the negative of the square root of 2 plus 1 over x squared divided by 3 minus 5 over x. And then as we apply the limit laws, this simply becomes the negative of the square root of 2 over 3. So that would be the output as x approaches negative infinity. Okay, now let's continue on. So this function obviously has vertical asymptotes. So how about the limit as x approaches 5/3 from numbers bigger than 5/3 of the function, which I'll rewrite here. To x squared plus 1 divided by 3x minus 5. Now, okay, so x approaches 5/3 from numbers bigger than 5/3. Well, 5/3 is in the domain of the numerator, and it's going to be some non-zero output. So the impact would be in the denominator. All right, so as x approaches 5/3, what's going to happen is we're going to get very, very close to 0 in the denominator, right? So we're going to get very, very close to 0, but we're approaching 0 from the right. That is, we're approaching 0 from positive numbers. So what's going to happen in the long run is we're going to have some finite number divided by a very tiny positive number. And so that basically amounts to infinity. Okay? Now conversely, if we let the limit as x approaches say 5/3 from the left, that is from numbers less than 5/3, well, again, the numerator will be non-zero in the limit, but the denominator will approach 0 from numbers less than 0. So we'll have some finite non-zero number divided by a very tiny negative number this time, and so that would be negative infinity. So now we know how to draw the graph of the function around the vertical asymptote 5/3, x equals 5/3. So knowing these three asymptotes, we have a pretty good idea as to how to sketch the graph, and I'll show it right here. Of course, there are other properties of the graph that are important, but we don't have enough machinery yet to actually understand the complete shape of the graph. But I'll give you the general idea, just using asymptotes alone, what the sketch would look like. So let me paste it into the smartboard. So it'll basically look like this. Okay, so there's the graph. And so check. As x approaches 5/3 from numbers bigger than 5/3, it shoots up toward infinity. As x approaches 5/3 from numbers less than 5/3, it shoots down toward negative infinity. We said that the square root of 2 over 3 was a horizontal asymptote, as well as negative square root of 2 over 3, and you can see that depicted in the drawing. What's interesting, though, is why does the graph exhibit this kind of elevation right here, and then it drops again? So no, it seems to be going up and then going back down around the y-intercept. And so we'll have to wait until chapter 4 before we understand why the graph is shaped the way it is. Okay. All right, so an interesting example. All right. So let's do another limit problem. Some more examples. So I wish to find the limit as x approaches infinity of the square root of x squared plus 1 minus x. Okay. All right, so this one needs a little bit of explanation. I'm sorry, not, is it infinity? Yeah. Is it infinity? Yes, it's infinity. I think there's an error in the online notes. I have x approaches 0, but that should be x approaches infinity. Now, supposing we use direct substitution in an abstract way. And if we were to do so, we would have basically what results in an infinity minus infinity case. Well, infinity minus infinity is another one of those peculiar indeterminate forms for the limit of a function. And when we have an indeterminate form, we typically can find a numeric result for the limit. Okay, and so we have to justify that. So the way we deal with this is we multiply this function by 1, and the numerator of 1 will be the conjugate of the function, and the denominator, of course, will be the conjugate of the function. So what I'm going to do is I'm going to make an adjustment here. I'm going to basically convert this function to a rational function by multiplying the function by its conjugate and dividing by its conjugate. So here's the function. Now I'm going to multiply by its conjugate. Which would be this. All we do is flip the sign. And of course divide by its conjugate, so we don't alter the function. Okay, and so this is equal to the limit as x approaches infinity of what? X squared plus 1 minus x squared divided by the square root of x squared plus 1 minus x. Okay, and so after simplifying, that becomes the limit as x approaches infinity of 1 divided by the square root of x squared plus 1 minus x. Now, that seemed like a lot of work and we still haven't achieved anything. We still have an indeterminate form in the denominator. But what we want to do is we want to transform this result into a function that conforms to the pattern of the limit as x approaches infinity of 1 over x to the r, the theorem, that is. So to do that, to achieve that end game, I'm going to multiply upstairs and downstairs by 1 over x, like this. So if I multiply upstairs by 1 over x, I'll have to multiply downstairs by 1 over x. Okay. And I get this result. And now I let the radical in the denominator absorb the 1 over x. So I used a technique from the previous examples to absorb the 1 over x into the radical. And so that would be the square root of 1 plus 1 over x minus 1. And then I used the theorem. And we know the numerator would go to 0 by the theorem and the limit laws. And the denominator would go to, let's see, I think that should be, oops, that should be plus. I'm sorry. Make this correction. That should be plus 1. Sorry, I had a sign flip there. Yeah, okay. So now that would be 1 plus 1, which is equal to 0. Okay, so the limit is in fact 0 for this problem. Okay, and to show you that we're not subtracting to infinities, although it looks like it, but we're not, we can examine the graph. So let's look at the graph of this function. And here it is. So clearly, as x approaches infinity, the output goes to 0 for this function. All right. So we're not subtracting to infinities. We're in fact following the properties of the function. Okay. So now let's talk about the exponential function, y equals e to the x, and evaluate its infinite limits. Right. So next page. And let me paste the function in. So I'll build a function table for the exponential function e to the x, and we'll examine its infinite limits based on a function table. So here we have the red graph showing y equals e to the x from algebra. And what we're interested in knowing is the limit as x approaches negative infinity of e to the x. Okay. And so by the function table, you can see that as x grows very, very small, that is toward negative infinity, observe the patterns of outputs. They're getting closer and closer to 0, and that's validated by the graph. So this limit is equal to 0, right? And so that brings up the next problem, and that is we can change the index of the limit. I'm calling this piece right here the index of the limit, right? What if we were to say the limit as x approaches 0 from the left of e to the 1 over x? Okay, so obviously for this function x can't be 0. But what happens is if we get closer and closer to 0 from the left for this function. Well, if we did that, then we're using negative numbers. Okay, so we're using negative numbers, and remember, if an exponent is negative, okay, if an exponent is negative, it sends it to the denominator, and so the transform problem would look something like this. If we were to approach now 0, this is the same problem. I replace x with negative x. And then when I do that, I approach x from numbers bigger than 0. And of course, as x grows smaller and smaller, this number, the exponent, goes bigger and bigger, and the denominator grows bigger and bigger, and so this becomes 0. All right, so that's one way of looking at it. But the better way of looking at it is to transform the limit into 1 of infinity. So this way is okay, but it's not the best way. It's not the most efficient way. The most efficient way is to change the exponent, to parameterize the exponent. So if we let variable t equal to 1 over x, all right? Let's do that. Now, so as x approaches 0 from the left, as x approaches 0 from the left, okay, what happens to t? Well, think about the graph of the hyperbola. As you approach 0 from the left, the hyperbola output goes to minus infinity. Okay, so we get this. So as x approaches 0 from the left, t approaches minus infinity. So we can transform the problem. We can change the rational function of the exponent, which is hard to solve, like this. We can replace 1 over x with a more stylistically pleasing expression in t. Okay, so as x approaches 0 plus is the same as t approaching minus infinity of e to the t. Okay, and based on the function table, based on the graph, we know that as t goes to minus infinity, this output goes to 0. Okay, so there it goes. All right. Now another interesting problem is, how about the limit as x approaches infinity of sine x? Okay. Well, we don't know, because as x grows very, very large, sine x cycles through the full range of values from -1 to 1. So we can never nail a particular value for the sine function. And this is due in large part to the fact that the sine function has no horizontal asymptotes, nor vertical asymptotes. Okay. All right. So the other part of our discussion on infinity would be infinite limits at infinity. So I think I can, so let's go back up to the graph. And what happens, what about this problem? The limit as x approaches infinity of e to the x. Well, clearly, as x grows larger, so does the output. So that's infinity. Okay. How about y equals x cubed? Okay. So as x goes larger, the output grows larger as well. So y approaches infinity. And you can visualize that just by graphing the function. Okay, so next page. In infinite limits at infinity. All right, so how about an example? We can do this best by example. Say the limit as x approaches infinity of x squared minus x. Okay, well, again, as per the previous example, you can't use direct substitution here because you'll be subtracting 2 infinities, and we said that the subtraction of 2 infinities is indeterminate. So what we can, the way you solve this problem is you factor it. Okay, so this would be the limit as x approaches infinity of x times x minus 1. and then we can use the limit laws. You can never subtract infinities, but you can always multiply the two. Rather strange. And we'll see why later on in the class. Okay, and of course this would be infinity. Okay, all right. How about the limit, and one more example, and then we'll move on to definitions. The limit as x approaches infinity of x squared plus x divided by 3 minus x. Okay, so we can recast this function in powers of 1 over x by dividing upstairs and downstairs by 1 over x squared. So that would be 1 plus 1 over x. I'm dividing upstairs and downstairs by x squared. Dividing upstairs and downstairs by x squared. And we get this. And then using the limit laws in the theorem, we have 1 over, oops, that doesn't work, does it? So my choice for division of upstairs and downstairs by x squared doesn't work. So scratch that, that doesn't work because we end up dividing by 0. We can't paint ourselves into that. So the other choice, we have to go to an alternative, and that is to divide upstairs and downstairs by 1 over x. Okay, so we can't use the theorem completely for this function. This function has some exceptions. So if we divide upstairs and downstairs by 1 over x with the hopes of achieving a format that where the terms are in terms of powers of 1 over x, all we can achieve is something that looks like this. And so this would essentially be infinity over 3, or excuse me, negative 1. That would be infinity over negative 1. Because 1 is inconsequential for large values of x, and by the theorem that goes to 0, so we're left with negative infinity as the limit. Okay, so that was kind of a tricky problem there. All right, so now we're going to do proofs, epsilon delta proofs for infinite limits. And I'll start off with a definition. I'll give you the epsilon delta definition for the limit as x approaches infinity, and here it is. Give me a second to paste it in to the smartboard. A couple of things I need to paste in the smartboard. Is that everything? I believe so. Okay, yeah, I think that's all I need. All right, so the definition, the limit as x approaches infinity, equaling to a number. All right, so the first criteria is the function has to be defined on some interval, a to infinity. Okay, in other words, it has to be defined as x approaches infinity so that we can achieve a numeric output. And what it means is that for any positive number on the y-axis, call it epsilon, there's a number n, okay, some number n on the x-axis, such that if x is bigger than n, then the distance from L is less than epsilon. All right, so here's the graphical interpretation of this definition. You choose some number n, okay, and if this, as x goes very, very large, if x goes very, very large, in other words, if x exceeds n, then what happens is the output for these values of x, Okay, the output, you choose any value of x bigger than n, this n here, and then you plug it into your function, then the output of the function will be within this band defined by L plus epsilon, L minus epsilon. You see this strip right here? The output is going to fall somewhere in this range, provided that x is bigger than this big N. So if you're trying to prove this result, the strategy is you need to identify what this big N is. Okay? If you can find such a big N so that for any x bigger than this big N, your output will never stray outside of this range, this very important range, L plus epsilon to L minus epsilon. Right? So you can see a proof emerging here. And so conversely, we can give the definition for the limit as x approaches minus infinity. All right, so give me a second to post that into Smartboard. So let me grab the picture from the textbook. All right, so now as x approaches minus infinity of a function equaling to a number, so clearly the function has to be defined for large values of negative x, for large negative number, or in other words, as x approaches negative infinity, the function has to be defined. And it stipulates that if we choose values of x that are less than this n right here, and we plug it into the function, then the function will range from along this interval on the y-axis. The outputs will never stray beyond this. The output will always be somewhere on this interval, this output interval. And so the trick is to proving that this limit exists would be to find this particular value of n. If we can find an n such that the output never strays beyond this interval right here, then this limit exists and is some finite number. All right, so let's do an interesting problem here. Let's actually go ahead and compute an n value. All right, so let's do that on the next problem. We want to find this. Suppose I want to calculate a value of n such that the distance, and let me give you an f of x, say 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. Okay, so this is a rather complicated function. And the distance between the output of this function and, say, 0.6. Okay, we want to find a value of n so that the distance between this output and the line y equals 0.6 never strays above or below 0.1. So how do we solve that? Do we know what the problem means? Of course we do. So to solve this problem, we can transform it into one without absolute value, and so that basically means we get this. So let's recast the problem, reformulate the problem into one without absolute value. Okay, so 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1 minus 0.6. So by definition of absolute value, being less than a number, we can do this, and then we'll add 0.6 to everybody. And so we have the output of the function being wedged between 0.5 and 0.7. All right, so what interval on the x-axis achieves this result? All right, so that's what we would like to know. So how do we do that? How do we find an interval on the x-axis so that the output of this function is wedged between 0.5 and 0.7? Well, the obvious technique is to use a calculator, a graphing calculator. So let's insert the graphing calculator. No, I don't want that one. I think that's DMOS. Is it Desmo? I forgot what it was called. Let me check. I forgot what the name of the calculator was. Yeah. Oh, I have too many T's, I see. 2 T's, right? Okay, so let's try that. There we go. Try it again. And let's type the URL. It's http://desmos.com/calculator. Okay. All right, so let's first graph the function, the rational function. So we have y is equal to 3x squared minus x minus 2 divided by, that was 5x squared plus 4x plus 4x plus 1. All right, so here's the graph of the function. It's this rather peculiar shape function, and it appears to be continuous for all values of x. Right. So now we want to define the range or the interval on the x-axis such that the output is less than 0.7, which is shown in blue, and the output of the function is greater than 0.5. So let's graph the line y equals 0.5. I should make that y equals 0.5, and that's shown in green. Okay, so where do we slice the interval? So I'll have to zoom in. So let me zoom in to the let me collapse this part so we can see more detail. So pan it here, get some more detail, zoom and pan, right? So it appears that the red curve stays confined within the strip, starting perhaps maybe right about at this value of x, subject to interpretation, right? So this appears to be what? 2, 4, 6, that's 7 minus 7.25 here, approximately. So So in this case, here's the value of n, such that if x is bigger than negative 7.25, okay, then we can guarantee that the red curve will stay between 0.5 and 0.7, all right, on that side at least, because of the asymptotic nature of the green lower bound of the strip. All right, so now let's find the right endpoint for the interval. So let's pan over. Pan over. It'll let me. Okay, so say starting right about here, perhaps at this point, at this value of x, it appears that the red function is bounded below by the green bar horizontal asymptote and above by the blue horizontal asymptote. And so this appears to be 7.25. So we can approximate the interval from negative 7.25 to 7.25. That the output of the function, well, okay, so wait a minute here. So we decided that we didn't want the output to be 0.1 within, say, 0.6. Okay, so that means actually, in fact, we only have one value of n, because here's why. Here's why. Let me pan back. You see, if x is less than 7.25, the function actually can be above 1. Okay, and so we don't want that. We want the function to be as close as possible to the line y equals 0.6, right? Because we want the distance between the function and 0.6 to be less than 0.1. So the only way that distance can be less than 0.1 at least is if x were greater than 7.25, as shown here. Or x were less than 7.25. Okay, so we actually have two line intervals that we can use. So if x is, so we can say if x is greater than 7.25, then the function's output will be no more than 0.1 from an output of 0.6. Or if the value of x were less than negative 7.25, then the output of the function will be no more than 0.1 units from 0.6. So that's what that means. Okay. All right. So yeah. So I think we got it there. All right. So let's do a proof involving infinity. So we want to prove, using the definitions of infinity, that the limit as x approaches infinity of 1 over x is equal to 0. Right? And so the way we can prove that is, well, let's motivate it graphically first. Let's motivate it graphically. So the way we can deal with that, let me draw some pictures, or pull some pictures from the text. One second. So we want to prove the limit as x approaches infinity of 1 over x is equal to 0. All right, and here's an epsilon delta structure. So if epsilon say equals to 1, right, and we choose n equals to 1, then we see that for any value of x greater than 0, or that is, excuse me, any value of x greater than n, the output will never let's see. The output of the function minus 0. Okay, so the output of the function f of x will never be greater than epsilon equals to 1. All right, so for this particular value of n, the output will never go above 1. All right, so how about we make epsilon smaller? And so say 0.2. And if we choose n equals to 5, then we'll see that the output of the function for x greater than 5 will never go above 0.2. All right, you see how that works? So the idea is to find this n. All right, we want to find an n for all epsilon. Now, say if epsilon is 0.1. Well, if n is equal to 10, then the output of the function never goes above 0.1. So you see the understanding here? So now if we chose epsilon, say equal to 0.000001, then n would be what? 1 million. And if n is 1 million, then we know that the output of the function never goes above 1 over a million. And so you can continue this on forever and ever, and then finally the output simply will degrade to a number very close to 0. So here's how we can put it into language, mathematical language that is. Here's how you would write it. Our grammar lesson for the day, right? Our English lesson for the day. So we have, as before, given epsilon greater than 0. Okay, and that's any epsilon greater than 0. The 3 drawings are 3 examples of epsilons. So we want to find an n preferably in terms of epsilon, such that if x is greater than n, okay, then the function 1 over x minus the limiting value 0 is less than epsilon. And this n has to hold for all positive epsilon. Okay, so how do we calculate n from this statement? That's what we need to find. If we can find an n, then the limit exists. So to calculate the n, make an assumption. Since x is growing very, very large, assume x is greater than 0 at the outset. Since this is an infinite limit problem, we're safe. That assumption is valid. Okay, so if that's the case, this implies that 1 over x will be less than epsilon. If and only if x is greater than 1 over epsilon. All right, so there you have it. This piece right here matches this piece right here. All right, so there's your choice for n. Choose n equal to 1 over epsilon. Okay, so if x is greater than n, which is equal to 1 over epsilon, all right, then what? 1 over x minus L, which is equal to 0, which is equal to 1 over x, is less than epsilon. All right, so long story short, our value of n is 1 over epsilon. And so epsilon is for any positive number, epsilon, we can find a corresponding n. And that's it. That's how you deal with it. Okay, and so the last concept for limits would be the limit as x approaches infinity of a function equaling to infinity. What is the definition for that? So let me post the definition in the illustration. It's somewhat trivial. I think you pretty much have an intuitive understanding of what it is by now. So bear with me while I post the picture. Okay, and so let f be a function defined on some interval a to infinity. The limit as x approaches infinity of the function is equal to infinity if, okay, so we find some n. If x is greater than n, then the output is greater than some m. So improving this limit, we need to find two numbers, an n and an m. So if x goes this way, then y can never be less than m. Okay, we have to find a corresponding m for the given n. Right, so that's all I'm going to do with this particular one. There are more efficient techniques for proving the limit as x approaches infinity of f of x equals infinity, which we'll discover later. Right. Okay, so with this we have completed section 2.6, and you now have enough tools to again complete your project number 2. So if you haven't already started, please get working on project number 2, and also please do your WebAssign. So in our next lecture, we'll pick up with section 2.7 of the text, which is essentially a discussion on the definition of what derivatives of functions are. So that's the end of this particular lecture.